Topic 1. So first of all, we need to make sure that we know all 8 type of energy stores, and also knowing a few examples. So for example, for gravitational potential energy, you know when an object goes up into the sky, for example a plane, or let's say when you throw a ball into the sky, that ball or that plane gains gravitational potential energy. Chemical energy is found in batteries, it's found in food, it's also found inside human beings. You've also got elastic potential energy. This is when let's say you have a rubber band, you stretch it out, and just before you let go, it has that potential to snap. So it has that elastic potential to snap back into place. Kinetic energy is the energy of moving objects. So these are all the different types of energy stores. Then we have energy transfer. So for example, we know that energy cannot be created or destroyed. It only goes from one form to another form. And you have to be able to explain how it transfers from one form to another form. So these are the 4 different types of energy transfers: by radiation, by heating, mechanically, and electrically. So we'll look at some examples and see how that applies. If you look at this person over here, the person is throwing a ball up into the sky. Now, what kind of energy transfers are going on? So the person inside him, he's got chemical energy that comes from the food he ate, or basically from the food that he ate. He's got chemical energy. Now that chemical energy from the person is being transferred into kinetic energy into the ball, and the way it's being transferred is it's being transferred mechanically. Then the kinetic energy of the ball, as the ball goes up, it's being turned into gravitational potential energy. So again, that's been done mechanically as well, because it's going against gravity. If we look at this scenario, the car is smashing into the wall. Now the car has got kinetic energy. As it smashes into the wall, you can see that this person is bouncing back. So there's a bit of elastic potential energy. Also, we know car crashes are very loud, so a lot of energy is being removed from here, or is being taken away, or radiated rather, by sound. Again, if you were to put your hand over here after the crash, you'll feel that it's quite warm. So there is also some thermal energy. So we went from kinetic energy into elastic potential energy because of this bouncing part, also into thermal energy, and also some energy was radiated away by sound. So let's look at another example. Let's say we have a basketball. Now, let's say the basketball is dropped from a certain height. Now, at this height, this basketball has 100 joules of gravitational potential energy. Now, the moment it drops, all that gravitational potential energy starts to decrease, and instead it's turning into kinetic energy. So just before the basketball hits the ground, it will have 0 gravitational potential energy, but it will have 100 joules of kinetic energy, because remember, all of the energy is being transferred from one form to another form. Now, we know that when basketballs hit the ground, they usually bounce back up, and the reason behind that is because as it hits the ground, that kinetic energy is being transferred into elastic energy. So the basketball gets smaller, and then it flies back up. Now, we also know that when the basketball goes up, it doesn't return back to the same height. The reason behind that is because as it hit the ground, some of the energy was turned into thermal energy, and also a bit of sound energy. So again, as the ball is going back up, the elastic potential energy turns into kinetic, which is why it's going up, and this cycle keeps on continuing, and eventually the basketball doesn't go up anymore. And the reason behind that is because every time it bounced, a lot of energy was wasted as thermal and sound, and over time the amount of energy remaining reduced to close to 0. Now, these are really 3 really important formulas that you need to know. The first one is for kinetic energy. Again, remember, the units for energy is joules. It's very important that you make sure that you use the correct units. So for mass, for example, it has to always be in kilograms. A lot of people use grams, and that's where they lose marks. Also, for speed, it has to be in meters per second. Another word for speed is velocity in this scenario. Gravitational potential energy, mass again in kilograms. G stands for the gravitational field strength. Now on planet Earth, that is 9.8. So G is basically 9.8 on planet Earth. Unless they specify it's on a different planet or maybe on the moon, then they'll tell you the different value for G. H is the height of the object, so how high it is being raised. This is elastic potential energy. So, for example, when you stretch a spring or when you compress a elastic object, it gains elastic potential energy. Okay, power. Now, power is a measure of energy transfer. Now, power is measured in watts. 1 watt means 1 joule is transferred every second. So, if you have, for example, 10 watts, that means 10 joules are transferred per second. If you have 100 watts, that means 100 joules of energy is transferred every second. So, power is just the rate of energy transfer, basically, how quickly energy is transferred. Now, look at these two cars. This one has 600 kilowatt power, whereas this one has 100 kilowatts. So this one can transfer more energy in the same amount of time as this one can. Now, if the car can transfer more energy, again, it means it will be faster. In this scenario, it will turn all of the chemical energy in the fuel into kinetic energy. However, the downside is that it will also burn through all their energy much more quickly. So if they both started with 1,000 joules of energy, the red car will be able to finish all their energy much more quicker. Okay, so conduction and convection are actually triple topics. However, I've decided to include them in here because I think it will help us to understand the following concepts afterwards. So first of all, what is conduction? Conduction is, you can think of it as a Mexican wave of energy going through a material. So the side that gets heated up first, that area, the particles will gain kinetic energy, they will begin to vibrate and collide with the neighboring particles. And by colliding, they will pass their energy to them. And then this keeps on happening throughout the material until energy is transferred all the way to the other side. So this is the definition for conduction. Okay, now remember, conduction happens best in solids, and the reason is because particles are closer together. However, in liquids and gases, you can say conduction hardly ever happens, and especially in gases, it's the least conductive. Now, when you're cooking, of course, you want to use a wooden spoon, and the reason behind that is although metal and wood are both solids, making them conductors, metal is actually a better conductor of heat than wood. And the reason behind that is not only because the particles are close together, obviously because it has metallic bonding, but also because it has electrons, and then those electrons can help to transfer the energy much more quickly. Wood, on the other hand, is an insulating material because although, again, it's a solid, however, there are air spaces between the particles, making it have low thermal conductivity. Convection, again, only happens in liquids and gases. It does not happen in solids because for convection you need moving particles. So the way it works is this. A liquid or a gas is heated up. When it gets heated, the gas particles or liquid particles gain energy, they move apart from one another and become less dense. As they become less dense, they start to move up. And now as they move up, there's already liquid or gas up here. So what they do is they displace them, meaning they push them down. So that cold liquid at the top gets pushed down and then it gets heated up again. And then the cycle continues, and this continuing cycle of heat is known as a convection current. Again, so convection only happens in liquid and gases. So the gas particles gain energy, they move faster, they move apart, become less dense and rise, and displaces the cooler gas or liquid from the top. Now, if you look at this picture was taken using an infrared scope or an infrared camera, and it shows us the different parts of the house and where energy is lost the most. So you can see over here, for example, in the roof and in the windows, there's a lot of energy loss, a lot of heat loss. So how can we reduce that? Now, normally, if you have a solid, having a single wall that's basically a solid. Now, through solids, heat is lost via conduction. However, how you could improve that is by having two walls. Now, if you have two walls, again, in between the two walls, you'll have empty space, which is basically full of air. So what's going to happen is heat's going to go through the wall via conduction, and then when it gets to the air part, it's going to move via convection. And this takes much more longer. Because it takes longer, that means that the heat remains inside the house for a longer period of time. Therefore, there's less heat being lost. So wall cavity, less conduction. Now, you can actually fill up that wall cavity with foam, and it'll look something like this. Now, the reason we do that is because although we know there's convection happening here, we can reduce that as well by having this cavity wall insulation. So now, having two walls and also filling up the airspace means there's also going to be less convection happening here. So again, that's even better if you want to keep the house warm for longer. Okay, double glazed windows. So you have one window pane. Remember, this is a solid. And then you have another window pane. and between them there's an airspace. So very similar to the two walls with air in the middle. Now this again helps to reduce conduction because you have two walls, two windows instead of having one solid. Why you wouldn't fill up the area in between is because although you could fill it up just like the cavity wall insulation, but the point of a window is for you to be able to see outside. If you fill it up with foam, then although it might be better at keeping heat in the house, it's not going to be a window anymore. Okay, draw excluders. What these guys do is, think about this, hot air sometimes can leave under the doors. Now to prevent that is what you can do is put a foam roll underneath the door, and what this foam roll will do is it will prevent the hot air from escaping. This is known as a draw excluder, and this is a cap. Now this table shows all the different types of ways that you can prevent heat from being lost from your house, and also how they do that. For example, conduction, convection, etc. So make sure you memorize all of these words because it could be easy 1 or 2 markers. Okay, efficiency. So any device, any electrical device, for example, a phone, a laptop, even let's say a crane or any machine that takes in energy, will also give out energy. Now, the way it gives out energy is that it can give it out in useful forms or as waste. So, for example, and of course this will depend on every machine. Now, let's look at this phone. It takes in 100 joules of electrical energy. It gives out 30 joules of light and 10 joules of sound. Also, the rest of it is given out as heat. So one of the rules is that you have to make sure that energy in is equal to energy out. So 100 in, 100 out. However, we can see that the device has transformed the energy. Now, from these three, we know that light and sound are useful because we have to use light has to come out so you can see your phone, and sound so that you can hear whatever you're listening to. Whereas thermal is a waste energy. You don't use your phone to heat up your hand or to keep you warm. So that's a waste energy. Now, if you were to calculate efficiency, that would be useful divided by total input. So in this case, it'll be 40 over 100. Now you can leave it as a decimal or you can times it by 100 to give it to you as a percentage. Now, friction, in most moving objects, friction is the reason why there's a lot of energy being lost, because friction leads to heat, and heat is a waste energy in most scenarios, except for things like radiators, where it's not a waste energy because you want to use a radiator to get warm. So how you can reduce friction is by using lubrication. This will reduce friction, so if there's less friction, there'll be less heat energy being lost, and therefore there'll be higher efficiency. So your machines will have higher efficiency. Now, energy sources are renewable or non-renewable. So we're going to look at the non-renewable ones first, but just make sure there's 2 of these. So you've got fossil fuels and you've got nuclear power, so such as uranium. That's the most common. Okay, so fossil fuel stations, the way they work, again, they probably won't ask you about this, but again, it's a good idea to have an understanding of it. So the way fossil fuel stations work is that chemical energy, so that's basically your fuel, your fossil fuel, is burnt. As that burns, the heat is used to heat up water. So inside these pipes over here, you have liquid water, and the heat turns that liquid water into gas, into steam. That steam then goes through the turbine, and it causes the turbine to spin. Now, this turbine is also connected to a generator. So when the turbine spins, the generator spins. Now, and then once the generator spins, that makes electricity, and then that's sent to the national grid. Also, what happens to the steam is that once it goes through the turbine, it then condenses back into liquid, so it can be used again. Also, look at these different energy transfers. Now, the same thing happens in nuclear power station, but instead of burning a fuel, we have nuclear rods which release heat themselves. So these uranium rods, for example, will heat up water. This hot water will then go and mix with another batch of water, which will then evaporate that, turn it into gas, and then steam spins the turbine, and then the turbine spins the generator, and then that makes electricity. So it's the same concept. These are nuclear and fossil fuel power stations. So you've got pros and cons. Now, pros, advantages are that you can make energy on demand. So basically, it's reliable. Or you can make energy whenever you want. Also, you can increase the energy supply. So, for example, if the city, for example, is binge watching Netflix and the electrical supply of the whole city goes up, you can actually burn more fossil fuels and increase the energy supply. Also, nuclear does not give off any dangerous gases. For example, it does not give off greenhouse gases or sulfur dioxide, which can lead to acid rain. Disadvantage is that both finite, so they're both going to eventually finish.
However, with nuclear, the problems is that it can lead to radiation, which is dangerous, and also nuclear has decommissioning time. So, for example, if you have a nuclear power plant and you decide to close it down, you can't immediately the next day open up a shop there, for example, KFC. The reason behind that is because although you've closed down the nuclear power plant, there's still some background radiation, so it takes a lot of time to slowly decommission it. Also, fossil fuels, the problems is that you can it releases carbon dioxide and sulfur dioxide. This is a greenhouse gas, causes global warming. This can cause acid rain. Chernobyl. So in this city there was a nuclear power station. Something went wrong. It exploded, and as a result of that, the whole city is now covered by radiation. So humans cannot live here for the next 20,000 years because of how much radiation. So this is one of the disadvantages of nuclear power stations. Okay, wind and solar, these are both renewable. So this is a wind turbine. It uses wind energy to create electricity. So wind goes and it spins the turbine, and then inside here there's a little generator. And solar panels, in here there's no generator, but basically a solar panel converts light energy directly from the sun into electrical energy. So advantages and disadvantages. So again, have a read of these, make sure you remember them. Now, geothermal, this is quite interesting. We know that the core of the planet is quite warm. So if you have a power station, what you can do is you can pump water down to the core, and then what that will do is it will heat. So the water remains inside pipes. The water heats up, turns into steam, and the steam comes back up, and it passes through a turbine, which then passes through a generator, and that makes electricity. So it's very similar to the fossil fuel and nuclear fuel, but instead of burning fuels or using a nuclear rod, we literally all we do is we use the Earth's heat to heat up the water. Hydroelectric. So here you have a dam. So you've got a valley which is quite high up. You fill up that valley with water, and of course a dam here to prevent the water from leaving. Once it's completely full, you can open up this dam, and then the water will rush down from up down into the turbine. So up here the water's got gravitational potential energy. When you open the tap, it will or open the gates rather, not tap, the water will rush down, so the gravitational potential energy is turned into kinetic energy. That then spins the turbine, and of course the turbine is connected to a generator, so when this spins, the generator spins, and of course that makes electricity, and it goes to the national grid. So advantage of this one, out of all the renewable ones, this one you can actually meet immediate demand. So basically you can increase the energy supply if required. Okay, topic 2. So first of all, we have a few keywords that we need to know and know their definition. Also, so current, rate of flow of charge, the units is amperes or amps, and the symbol in equations is little I, but of course the units is A. You got voltage. Another word for voltage is potential difference. You've got resistance and charge. So all of these, make sure you know their definitions, quite straightforward, and their symbols. Charge is coulombs, but the symbol is Q. Okay. Here you have a standard circuit. As you can see, there's a cell here. One of these is called a cell, but if you have two cells next to each other, that's a battery. Now, very important that you have to make sure they both have the same orientation. So like in this scenario, don't flip the other one. So you have to make sure they both have the same orientation. Also, the longer side of the cell is positively charged. So electrons always go this way. The charge travels in this direction, the current flows in this direction. This is known as a component. Now, there are many different types of components that you can have in a circuit. There's about 12 of them that you need to know. So again, cell, battery, switch. When it's like this, it's open, otherwise it will be closed. So here, no current flows, so the whole thing turns off. But here, current can flow. You've got a standard resistor, and of course you've got other ones as well. So look at all of these, pause the video, make sure you can memorize them. Now, so what we're going to do is the first practical, which is investigating how a length of wire can affect resistance. So imagine this. Let's say we have two circuits. Now, let's say they both have the same voltage supply, so 10 volts. And there's a formula that goes like this. V equals IR. So voltage equals current times resistance. We're going to talk about all the formulas afterwards, but for now, if I was to ask you, do you think that in the first circuit there's more resistance, or do you think there's more resistance in the second circuit? Now, you might think, okay, what's the difference? Well, the difference is that in the second circuit, there's much more wires being used. So the overall length of the circuit is much more longer. So how could we investigate that? Do we think there's going to be a difference, or do we think there's going to be the same? So the way we're going to do that is the following. Oh, don't know how we go back here. Oh, quite long. Sorry about that. Okay, so this is our setup. So here we have a electric energy supply. You can either use a battery or even a single cell, but again, make sure you know the orientation. This is a switch, and we need to use the switch to kind of change the length of the wire. So we have to turn it off when we're touching it. As you can see, the wire is continuously going like this. However, now we have crocodile clips, and then the electrons go from here into this wire and then back out. So here's your complete circuit like this. Goes like that. Okay, so what we're going to do? So what we're going to do first is we're going to put the crocodile clips right next to each other. So what we're going to do in the whole experiment, keep one stationary and move the other one backwards. And by moving this guy backwards, what we're going to be doing is we're going to be increasing the distance that the electrons will have to flow. And of course, we have a ruler here so we can measure how long we've increased the distance for. A voltmeter and ammeter. The reason we have these two is because we're going to use the formula V equals IR to find the resistance. So remember, resistance now is going to be equal to, when I rearrange V equals IR, that gives me V over I equals R. So voltage, current, I calculate those, and I measure those, and then I can use them to calculate my resistance. So eventually I'm going to plot length of wire on the x-axis, and I'm going to plot resistance on the y-axis. Now you should theoretically get this line, a straight line, and this shows us that as the length of wire increases, so does the resistance, which means that they are directly proportional. Now, how would you explain this in your exam? So let's say you have a 6 marker. How would you explain it? So here are the points you should mention. Number 1, you say attach your crocodile clips to the test wire 0 centimeters apart. So literally, they're going to be next to each other, these two crocodile clips. The voltmeter should always be in parallel, and the ammeter should always be in series. Then you turn on your switch. So you turn this on. So you close that, turn the switch on, and then you measure what the values on the voltmeter and on the ammeter. Okay, so turn on the switch and measure voltage and current. Then you can use V equals IR to calculate resistance. Then you turn off your switch. So you turn this off, you open it again, and then you take, so you keep one of these crocodiles in place, and you take the other one and you start to move it back. And then you close your switch, and then you measure again, and then calculate R. Then you open switch, move it back, close the switch, measure, calculate R, open switch, move back, close switch, measure, calculate R. So you keep doing that. So so turn off switch, move crocodile clips, repeat steps 3 to 5 until all the wire has been used, and then you're going to plot length of wire versus resistance, and it should be directly proportional. Now, if they ask you how could you make sure your results are reliable, mention these points, because over time the wire may heat up, and we know temperature can also affect resistance. Leave the switch off until wire cools. So basically, between your readings, when this is on, sometimes the wire could heat up, and that could mess up your results. So between your readings, you would leave this off, let everything cool down, and then start again. Also, keep the thickness of the wire constant. And if they ask you, explain why, let's say your graph looks like this. So it doesn't go through 0 like this one does over here. The reason could be that initially your two crocodile clips were not exactly 0 centimeters apart. Even if they were like a millimeter or 2 millimeters apart, your data will not be straight like that. So these are some potential questions they could ask you. Moving on. Okay, so the next practical. Now in this topic we have loads of practicals, by the way. Next practical is calculating IV characteristics. IV stands for current voltage characteristics of different components. So components include, going back to, so like a resistor, that's the main one, filament, lamp, and diode. So we're going to be testing how these three mainly, how they behave as you put different amounts of current through them, different amounts of voltage through them, and you measure their current. Okay, again, this is really easy practical. So first of all, here we have a standard test circuit. In fact, what I'm going to do. Okay, so here is our standard test circuit. Now, this circuit is what we're going to use to carry out the practical. So if they ask you to draw a standard test circuit in your exam, this is exactly what you want to do. Okay, so here's your energy supply. You've got something called a variable resistor. This is the component that you're going to be testing. Now, you also have to have the voltmeter always going parallel around your component. And then, of course, the ammeter is going to be in series. Now, remember, the whole point of this experiment is to see how this component, as you give it different amounts of voltage going through it,
how much the current will change by. Okay, so now the battery or the cell, in this case it's a battery, will have a set voltage. So for example, let's say here it says 10 volts. That means that this battery or cell will can only give 10 volts to the component. Now we want to change the voltage every time. So instead of changing the battery, all we can do is we can keep that, but then use a variable resistor. And what this will do is this will control how much from that 10 can pass through into the component. So what we're going to do is we're going to change the amount of voltage that the component is getting, and then we're going to be measuring what the current says. So we could say that our independent variable is voltage, that we're going to pass through the component because we changed that, and then our dependent variable, the thing that we measure, is going to be the current. Okay, so we're going to set the variable resistor to maximum resistance, so to only allow, let's say, 1 volt from that 10 through to the component. Then we measure what the ammeter says. So imagine the ammeter might say 2. So when 1 volts go through, the current is 2. Then we change the resistance of the variable resistor to now let a bit more voltage. So we reduce the resistance so a bit more voltage can pass through. So let's say now 2 volts can pass through. And then we record what it says on the ammeter. So it might say 4 amps. And then we keep doing that. So we keep doing that until we finally get to 10 volts. And of course, we're going to be measuring what the current says. So for 1, 2, all the way up to 10 volts. Okay, once you've done that, then what you want to do is you want to plot this. So you have voltage on the x-axis, current on the y-axis. Now, if you plot it, your graph should look like this. You have x on the x-axis, you have voltage, and y is current. And you should see a pretty straight line. However, what we want to do is we want to see how it behaves on the other side of the graph as well. So how do we get the values for this side of the graph? So the way we're going to do that is once we finish the practical, we take the component out and then we flip it. So we change its directions. So you can say we swap the ends of the component. And then you do the same practical from the beginning. So again, you're going to write your data, voltage, current, etc. And once you've done that, you plot that on this side of the graph. Okay, and then there's your complete IV characteristic graph. Right, so once you finished your graphs, you can see that here you go. This, for a standard resistor, we get this type of graph. For a filament lamp, we get this graph, which is it's almost like an S shape. And for a diode, you have this graph. So the way you can explain that is for a filament lamp, as voltage increases, so does the temperature. When temperature goes higher, so does the resistance. So that's why it begins to flatten off. So here at the flat point, and here as it gets flatter, the resistance is much higher. For a diode, one side, the resistance is really high. On the other side, as you increase the voltage, the resistance becomes lower and lower as it becomes more and more steep. Now, if you compare these two, they might ask you in your exam to explain which A or B has got higher resistance. So this is the rule. Resistance is 1 over the gradient. So in other words, if the line is steeper, that means the resistance is lower. So for example, A right now has lower resistance than B. If they ask you to calculate it, so pick 2 points on the line, calculate the gradient. So imagine, let's say this was 4, that was 2. So the gradient is going to be 4 over 2, which is 2. And then to find resistance, all you do is you do 1 over the gradient. So 1 over 2. So that is going to be 0.5 ohms. Okay, so resistance is 1 over gradient. So the steeper it is, the lower the resistance. Now, sensing circuits. So sensing circuits are used in, for example, automatic night lights or in automatic fans that turn on when your computer gets too hot. So you don't actually have to do anything. The component itself will detect the surroundings when the conditions change, and it will automatically turn the circuit on or off. Now, you've got 2 main types of components which are included in sensing circuits. You have LDRs, which are used in circuits involving light, and thermistors for circuits involving heat. So with LDR, as you can see, the resistance changes based on light intensity, and for thermistor, resistance changes based on temperature. Now, a good way to remember that is LDR, when it's dark, it's scared, so it can't move. Can't move means high resistance because it doesn't flow. So LDR in darkness, high resistance.
Of course, therefore, in brightness, it can, it's not scared anymore, it can run. It's not really scared, I'm just saying a good way to remember that. Now, thermistor. Thermistor, when it's cold, it's freezing. Again, freezing, can't move, high resistance. So when it's hot, it can flow nicely, and therefore the resistance is low. Okay, make sure you don't say scared or freezing in your exam. Just make sure it's just a good way to remember this pattern. Okay, so again, here's examples of what an LDR is used for. So these little lights turn on automatically when it goes dark, and thermistors are connected to fans in your computer. So sometimes if you use your computer for too long, you can hear like a little sound going on. That's because the fans have been activated, and how it knows that is because the thermistor has detected the temperature of the computer is getting so warm that it needs the fan to turn on. Now you have to be able to. So of course these are the two graphs, the two circuits. Now notice in both circuits, let's say on the left you have the circuit for an LDR. So here's your LDR, and here's the component that's going to be turning on, the bulb. And of course it has to have a fixed resistor. The thermistor, again, fixed resistor, and fan. Now there's similarities and differences. The similarities that they both have fixed resistors with them. The difference is that LDR is with its component, but a thermistor is not with its component. That's just how it's arranged because of the way it works. Again, you can remember that because a thermistor is not a fan of its fan. So they're not together. Okay, cool. So moving on. How do we explain that? So let's start with the LDRs one. Now, this is actually probably one of the most challenging parts of this topic. So I would recommend you maybe pausing and starting again or restarting the explanation. So first of all, here you have your energy supply. So let's say that is fixed to 10 volts. We know that the fixed resistor and the LDR are in series. So if they're in series, that means they're sharing the voltage. So let's say they both have 5, yeah, just for argument's sake. Now, the LDR and the bulb are parallel, which means that the bulb will copy whatever the voltage of the LDR is. So right now, since the LDR's voltage is 5, the bulb's voltage will also be 5. Now, what's going to happen is we want the bulb to turn on. So to turn on or to become brighter. Now, the voltage is equal to brightness. So the higher the voltage, the brighter the bulb becomes. So for example, if the voltage becomes like 9 volts, the bulb will be much more brighter. Now, how do we explain how this works? So step 1, when it becomes dark, who is the first component that will react to that? Of course, the LDR. So the LDR's resistance will go up. When the LDR's resistance goes up, that means the total resistance in the whole circuit will also begin to go up as well. Now, we know the total voltage is equal to total current times total resistance. So that's for the whole circuit. Since the total voltage is fixed at 10 volts, we know that V is not going to change. So if R has increased, if the total resistance has increased, to match that and to ensure that V does not change, I has to decrease. So now we know that the total current in this whole circuit has decreased. Okay, so we know that the total current has decreased. Now we're going to look at the fixed resistor. So for the fixed resistor, we know that its resistance is fixed. So it's not going to change. So again, for the fixed resistor, V equals IR. His resistance does not change, so we can ignore that. We can just cancel that out, which leaves us with, for him, V equals I. So now remember, this fixed resistor is inside the circuit in which the total current has just dropped. So that means his current has also dropped because he's going to be getting less current because he's in that same circuit. So if his current drops and V equals I, that means its voltage drops as well. So now this fixed resistor, let's say from 5 volts, it's going to get to 2 volts. Now, we know that the fixed resistor and the LDR are in series, which means that voltage gets shared. So if shared, for example, here you have 5, which makes 10. Now, if this guy's dropped to 2, the LDR has to now take more. So the LDR takes 8 volts. So the voltage of the LDR now increases. Now, since the LDR and the bulb are parallel, remember the parallel, that means the bulb is going to copy the voltage of the LDR. So since the LDR's voltage went to 8, the bulb's voltage will also go to 8. Now, we can see that the voltage of the bulb has increased. So the bulb's voltage has increased, which means that the brightness of the bulb
the brightness will also increase, and therefore the bulb turns on. So in darkness, the brightness increases. They could also ask you the same thing for what happens when it becomes brighter outside. So it's the same process, but you just say the opposite. Okay, now for the thermistor, it's the same concept. However, things are changing a little bit over here. So first of all, thermistors work to turn on a fan when it becomes hot. So the moment it becomes hot, the first component to react to that, of course, is the thermistor. Now the thermistor's resistance will decrease. So you have to remember that a thermistor in heat, the resistance decreases. Now also remember over here that this is fixed to 10 volts, for example, and that's shared between, let's say 5 volts for this guy and 5 volts for the fixed resistor. Yeah, I'm just using random numbers here. It might not be 10 in your exam. Now, so when it becomes hot, the resistance of the thermistor begins to drop. That means that the total resistance in the whole circuit also drops. And since V equals IR, so for the total voltage equals total current times total resistance, and we know that the total voltage is not going to change. So if the total resistance has just dropped, that means that the total current in the circuit will increase. Now, looking at the fixed resistor. This is the fixed resistor right here. For the fixed resistor, V equals IR. And again, because its resistance is fixed, that means that it will R, we can ignore R, and we can say V equals I. So if this fixed resistor is in a circuit in which the current has increased, since the current in the whole circuit has increased, that means the current in the fixed resistor will also increase. So if V increases, therefore that means, if I increases, that means V increases as well. So we just figured out that the voltage of the fixed resistor is going to increase. So instead of going from 5, it might go to 8. Again, this now becomes 2 volts because remember they get shared. Then the fixed resistor and the fan are parallel, which means that whatever the fixed resistor voltage is, the fan will copy that. So the fan's voltage also increases to 80 volts. And as a result, the fan speeds up. So that is the fixed resistor. Okay, so you have thermistor, and then you have LDR. So make sure that you memorize all of these points when explaining it. This could be a potential 6 marker. So this one's for the thermistor, and this one is for the LDR. If they could also ask you as a 2 marker, so they might say to you, explain if it becomes dark, what happens to the voltage of the LDR, or what happens to the thermistor. So if it says ask you for a 2 marker, you're going to mention these points. So for the LDR, if it becomes dark, resistance goes up, therefore LDR takes a greater share of the total voltage. And then in heat, the thermistor's the resistance decreases when it becomes hot. Therefore, the fixed resistor has to take a greater share of the voltage. So just memorize those points and you'll be good to go. All right, moving on. You have 2 types of circuits. We have series and parallel. So if you look over here, these components are end to end, making them a series circuit. Whereas over here, the components are side to side. So that is a parallel circuit. Now, you got voltage, current, and resistance. Those 3 features. So in a series circuit, voltage adds up. So for example, if this was 10 volts, that means that these 2 have to add up. So it could be 5 volts and 5 volts like that. Or it could be 1 and 9 or 2 and 8, etc. But they have to basically add up or get shared. You can say it should get shared. Current is the same everywhere. So for example, if this is 5 amps, the current here is 5 amps. The current here is 5 amps. Everywhere it's 5 amps. The current is the same everywhere. And then finally, resistance adds up. So for example, again, making up random numbers here. But imagine this is 3 ohms. And this is also 3 ohms. That means that the total resistance is going to be 6 ohms. Now, in a parallel circuit, the voltage is the same everywhere. So, for example, if that is 10 volts, this will say 10 volts, and this will say 10 volts as well. So you can see that the voltage does not get shared. It's the same in every component. However, the difference is that the current does get shared. So here, if the current, let's say, was 5 amps, then in these 2 branches, they'll have to add up. So for example, it could be 2.5 amps here and 2.5 amps over there. And then finally, resistance. In parallel circuits, we don't actually have to calculate it. However, they could ask you to calculate resistance for a particular branch, but they won't ask you to calculate the total resistance of the whole circuit. But the rule is that with parallel circuits, As you add more loops, the total resistance gets smaller. Okay, so I'm going to show you why adding more branches to a parallel circuit will decrease the total resistance. So right here we have a parallel circuit, and you can see there are two components. Now remember, voltage stays the same, so this will be also 10 volts, and this will also be 10 volts. Now let's give a value for the current. So let's say the current was 6 amps. That means it will be shared between these two. So it could be 3, or it could be 2, 4, etc. So just for simplicity, I'll make it 3, 3. So 3 here and 3 amps here. And again, this branch will be 6. So the way current works is that it comes down the main branch and then it splits into these two. So that 6 splits into 3 and 3, and then those two rejoin back, which is why you have 6 here again. Okay, so what we're going to do now is we're going to add another branch to this circuit and see what happens to the total resistance. Okay, now remember, to find resistance is equal to V is equal to IR, and R is equal to V over I. So keep that in mind. Now we're going to add another branch, let's say another identical branch to the next one. So right here, we're going to add another branch, just like this. And of course the numbers are going to change now. So let's say, so I'll quickly explain why the numbers change. Before, we only had 2 branches, but now we've added another branch, which means that the current has more space to go through. It's got 3 branches to travel across, which means overall, there's going to be more current traveling in this circuit compared to the one on the left. Since there's going to be more current flowing, that means the number on the ammeter is going to be a much more greater number. So it might be, let's say, 9. So 3, 3, 3, and then of course 9 again. Okay, so the rule is when you add more branches, there is more space for current to flow. Now remember, remember voltage is not changing. It still stays as 10. So V equals IR. We know that voltage does not change. If current has increased, to balance that and to make sure that the voltage does not change, the resistance has to decrease. So as a rule, if I was to ask you which of these two circuits, the one on the left or the one on the right, has a greater resistance, you say that the one on the left has less branches, so it has more resistance. The one on the right has more branches, therefore it has less resistance. So that is the rule for parallel circuits. Okay, now over here we have a practical. This practical is going to prove the idea that adding more resistors in series will increase the resistance, and in parallel will decrease the resistance. So what we're going to do is we're going to start off with a battery or a cell which has a set voltage. Then we have one resistor. We connect that, we measure the current. And then let's say we're testing for series. So then what we'll do is we'll add another resistor. So now we have 2, and then measure the current. And of course, since you have voltage and you have current, you can calculate resistance. And then you add 3, and you add 4, and you keep doing that. So basically, you're going to be adding more resistors. Each time you measure what the current says, and you use the formula V equals IR to calculate resistance. And you do the same thing if you want to start again from the beginning, and you can do the same thing for parallel. You add more resistors in parallel, you measure the current. Remember, the voltage is set, you measure the current, and you can calculate resistance. Once you got your data, you then plot it. So make sure you remember these points. And now your data should look like this once it's been plotted. So in series, as you add more resistors, in series, the total resistance should increase. But in parallel, as you add more loops and more branches, then the resistance will actually decrease. Okay, this is a plug. Now plugs have 3 main wires in them. You have a blue wire, which is known as the neutral wire, brown, which is the live wire, and green and yellow, which is the earth wire. Also, look at these numbers over here. So neutral wire is 0 volts. The earth wire is also 0 volts, and the live wire is 230 volts. Now, they might ask you to also show where they go. They might give you a picture and ask you to draw them. A good way to remember is the second letter of brown. So brown is the live wire. The second letter of brown is R. So R stands for right. And the second letter of blue is L, which stands for the left. So the blue wire goes to the left of the plug, and the brown or red wire goes to the right of the plug. The thing over here is a fuse, and we'll talk about how a fuse is used for safety purposes. And of course, at the top, you have the earth wire. Okay, so we'll talk about how a plug works to save you. So imagine here, so we've got a toaster, okay, Now, the brown wire brings current in. Okay, so it brings current in to the machine. And then the blue wire or the neutral wire takes current out. So live brings in and neutral brings out. By the way, the amount of current or voltage entering is 230 volts and 50 hertz. So make sure you remember these two numbers for the brown wire. Remember, blue and green are neutral. They're zero. Everything's zero. Okay, so brown or live brings in and blue or neutral takes out. Now, sometimes what can happen, and of course you can see over here, the green one is actually touching the metal casing itself. So the earth wire is actually touching the metal casing itself. And we're going to talk about how this works. So sometimes what can happen is with the brown wire, a fault can develop in which the brown wire or the live wire touches the casing itself. When that happens, the entire apparatus, so the entire casing, also becomes live. So everything becomes live. Now, if at this point you were to touch the metal casing, you would also get an electric shock. Now, how does the machine prevent that from happening? So, although you have all this extra current going to the casing, the earth wire will now step in and it will take up all of that current and remove it and send it out to the earth. So the earth wire is basically going to help to remove all that current that is passing through the metal casing. So that's the first thing. The second thing is that over here we also have a fuse. So the fuse looks a bit like this, going back. This is the fuse. So what you say is, the moment that the live wire touches the metal casing, the current in the live wire increases. Okay, so the current in the live wire increases. Now this fuse acts like a gate. So it has, like, for example, it will have a fuse rating on it, let's say 5 amps. Which means that it will allow a maximum amount of 5 amps to enter through the live wire. But we know that if there's a fault, more current is going to try and enter, more than 5. And then the fuse at that moment will blow. When the fuse blows or melts, then it cuts off the amount of the electricity coming in. And then, of course, that helps to prevent you from getting shocked. So again, how would you explain that? So these are the main points you have to mention. If you mention all of these points, that's good enough to score the marks for explaining that topic. Okay, moving on, national grid. So the national grid this is the definition of national grid, a system of cables and transformers. So cables are these things that are going around over here, and then these things over here are the transformers. Now, initially, in the national grid, electricity used to be sent as high current. So there'll be high current traveling through these wires, going from the factory to the person's home. But the problem with that was that although there's high current, there's also a lot of energy that was wasted as heat. So a lot of heat energy would escape to the surroundings. So imagine if you made like 1,000 joules of energy, maybe like 10 would get to the person's house, which is very inefficient. So instead what we do is, instead of using high current, we use high voltage. High voltage is much more efficient. It reduces the current, so less energy is lost. Now, with transformers, there's a formula that we need to apply. And before we talk about that, remember, there are 2 types of transformers. You have a step-up transformer, which increases the voltage, so that can travel across, and then a step-down transformer, which brings it down to safe levels before it enters your house. So it brings it to 230 volts and 50 hertz. So remember that voltage. That is what the step-down transformer turns it into just before it enters your house. Okay, so with transformers, this is the formula that you need to memorize. Potential difference is another word for voltage. So voltage in the secondary coil times current in the secondary coil is equal to voltage in primary times current in primary. So if you look at this picture over here, this is a transformer. Okay, the red one, so let's say the red wire is bringing current in. This is the primary coil, and the blue one is taking it away. That is the secondary coil. So you have voltage in the first one. So let's say let's say that the voltage in here is also, how would you know if this is a step up or a step down transformer? It's to do with the number of coils. So if you can see here, there are less coils in the secondary, which means it's a step down transformer. So if there were more coils in the secondary, then it would have been a step up transformer. So step down reduces voltage, step up increases voltage. So let's say the voltage here was 30 volts, and the current was 5 amps. Then let's say the voltage here is going to be 10 volts. Okay, and then I'll ask you, work out the current. What is the current in here? So the formula is this. number of voltage in primary times current in primary is equal to voltage in secondary times current in secondary. So you're going to say 30 times by 5 is equal to 10 times by whatever the current was, which we don't know, so we'll call that A. And then when you rearrange that, it's going to be 30 times 5 over 10, and then that will give you the current. Okay, topic 3. So the first part is talking about density. Now, density is mass divided by volume. So to find something's density, you need to know what its mass is, and you also need to work out its volume. Now, there are 3 types of objects that we have to work out the density of, so we're going to talk about them over here. The first one is if you have a regular solid. So let's say you have a regular solid. Now, how would you find its mass? So to find the mass, easy, you just take the solid and you put it on a weighing scale or a mass balance and you work out the mass. What about its volume? Now, because it's a regular solid, that means the size will be regular. So to find the volume for this guy, it's going to be 2 times 2 times 5. So that will give you 40. Let's say it's centimeters cubed. Let's say it was in centimeters. So you've got that, and let's say when we put it on the weighing scale, the mass was 10 grams. So then finally, to find density, you're going to do mass, which is 10 grams divided by 40. And that will give you the density for the first object. Now, what if the object is not regular? So let's say it hasn't got a regular shape. Like, let's say it's this rock over here. Now, this rock, we can work out its mass easily. Again, just like before, we put it on the weighing scale and we can work out what the mass is. But what about the volume? Because unlike the square box, the rock doesn't have regular sides. So in this scenario, what we do is we put it into something called a eureka can. So you take the rock and you're going to fill up a eureka can with water. Now, this eureka can has water up to the brim, and over here you have a little nozzle, and from this nozzle water can fall into the little beaker on the side. So what you're going to do is you're going to take this rock, you're going to throw it into the eureka can, and then of course as it goes in, the water is going to then, the level of water is going to increase and it's going to fall out into this beaker. So it's just like when, for example, when you get into a bathtub, when you enter, the level of water rises. So the rule is that this rock will displace the same volume of water as its own volume. So let's say the rock's volume is 20 centimeters cubed. That means when you put it into the eureka can, 20 centimeters cubed of water will be collected over here. Again, you have the mass from the weighing scale. Now you divide it by the volume from the eureka can, and there you go, you can work out density. Now the final one is, what about if you have a liquid? Because with a liquid, we can't really pour it into a eureka can because it will just fall out. So if you have a liquid, the method is a little bit different. So what we're going to do first is we're going to, again, we need to find mass. So how do you find the mass of a liquid? First of all, we're going to get a measuring cylinder, put that on a weighing scale, and then you're going to take your liquid. Now this is a liquid that we want to find the density, so we do not know what the density of this liquid is. We're not sure. So what we're going to do is we're going to pour out 10 centimeters cubed, and we're going to use the measuring scale, measuring cylinder, to work that out. So you're going to take this liquid, you're going to pour out 10 centimeters cubed, and that should fill up into the measuring cylinder. Now as it fills up, you will also see that it will tell you what the mass is. So it will say, for example, 15 grams. So there you go, you just worked out the mass and you've worked out the volume. The volume was 10 centimeters cubed that you poured out, the mass you got from the weighing scale, and then from that you can do mass divided by volume to give you the density. Now to repeat that, you can do another 10 centimeters cubed, and you can keep repeating and work out mass every time and then calculate an average. So again, those 3 examples are written over here. Okay, next one. This, again, I think we've mentioned this in chemistry, but just a good refresher of solids, liquids, and gases. So make sure you memorize the different points between them. Okay, now before we talk about this, I want you to consider a concept over here. Let's say we have a solid, and let's say that this solid is at 20 degrees Celsius. Now, we start heating up the solid, and of course, as we heat it up, the temperature of the solid increases. So it's gone from 20 degrees up to, let's say, 80 degrees. So the solid has become hotter. Now, after 80 degrees, we continue to heat it. However, we notice that the solid begins to melt and it turns into a liquid. Now, this liquid, again, is 80 degrees. Then we heat up the liquid. So the temperature of the liquid now begins to rise. So from 80 degrees, it goes to, let's say, 200 degrees Celsius. Once we get to 200, we heat it up even more, and then the liquid turns into a gas. What's the temperature of this gas right now? It's still 200 degrees Celsius. Finally, we have the gas and we keep heating it up and the temperature increases. Now notice energy is used in two ways. In one way, energy is used to increase temperature, so it increases temperature, but does not change the state of the material. So for example, the solid went from 20 degrees to 80 degrees. The temperature increased, but it's still a solid. And then in another scenario, we saw that energy is used to change state, but not temperature. So for example, when it goes from solid to liquid, it's changing state, but it's not changing temperature. It's still 80 degrees. So those two types of energies have specific names. So the second one was changing the state, but not changing the temperature. Okay, so when you increase temperature but don't change state, this is known as specific heat capacity. When you change state but don't change temperature, that is called specific latent heat. Those two words have different meanings. Make sure you don't get confused between them. Now, with specific latent heat, we can have two different types. We can have specific latent heat of vaporization, and also we can have specific latent heat of fusion. So vaporization is when you're going from solid to liquid, from liquid to gas. Fusion is when you're going from gas to liquid and liquid to solid. So those are the two types of specific latent heat. Okay. These points over here talk about what happens during freezing and condensation and what happens during melting and boiling. So make sure you memorize these points over there. Okay, now this is a heating curve and you have a cooling curve. So basically what we said before, we can see the flat bits is where the state changes but the temperature does not change. So the flat bits are specific latent heat. The diagonal bits is where the temperature is changing. That is specific heat capacity. So again, over here you have specific heat capacity, and over here you have specific latent heat. In this one, since you're melting, that specific latent heat of vaporization, specific latent heat of vaporization. Over here, when you're condensing and freezing, it's specific latent heat of fusion. Now, internal energy of any system, of any group of particles, is the sum of their kinetic energy and their potential energies. So that is the definition of internal energy. Now, if internal energy increases, so does the temperature of the particles. So if particles have more internal energy, their temperature increases. So we can summarize that and say that if particles have more kinetic energy, as a result, they'll have more internal energy, and since they have more internal energy, they'll have higher temperature. So more kinetic energy means higher temperature. So keep that in mind. Next, gas pressure. So what is pressure? Pressure is equal to a force divided over an area. Or you can just say for combined science, you can just pressure is when particles collide with the walls of a container. So as you can see here, there are particles and they move randomly. But whenever they move, they end up colliding with the walls of the container. And then that force they apply, the outward force, is known as pressure. Now, as a rule, the force is always, as you can see, these red arrows are always 90 degrees to the surface. So it doesn't matter which way the particles come, which angle they're coming from, whenever they collide, the force is always 90 degrees to the surface. And they always point outwards. Okay, now how does that work? The way it works is this: when particles come and collide into a surface, their momentum changes, which means they slow down, and that change in momentum is equal to force. Now, over here, we can talk about how increasing temperature of a gas increases the pressure. So, for example, let's say you have a balloon, and inside that balloon, there are gas particles. If you would begin to heat that up, what happens is the particles gain energy and they begin to move faster, and as a result, they create more pressure. So, how do you explain that? So, you say the following: particles gain kinetic energy. There's going to be because they move faster, when they collide with the walls, there's going to be a bigger change in momentum. So when they collide with the walls of the container, there's going to be a larger change in momentum. Because of that larger force, there's going to be more pressure, and as a result, the balloon expands. And as you can see, in both scenarios, over here, when you heat up the liquid, the particles begin to move faster. So when they collide, there's a larger force and more pressure, so that's why the balloon expands. Now, what if you cool a balloon down? So over here, in this scenario, this balloon is put into liquid nitrogen, which is really, really cold.
As you can see, over time, that balloon begins to shrink. And the reason behind that is the opposite of this. So here, it's basically going to be the opposite for when you increase temperature, the pressure increases. But if you decrease temperature, the pressure reduces. And of course, once that's happened, if you were then to take the balloon out of the liquid nitrogen and put it back on a table and heat it up again, you can see the particles gain energy and there's more pressure. So I'll definitely recommend you YouTubing in this particular title and watch the videos.
Okay, topic 4. Now, the first part is about the model of the atom. Now, we did this in chemistry, so just a quick reminder of DJ R&B, Dalton, J.J. Thomson, Rutherford, and Niels Bohr. Also, Chadwick, he helped to discover neutrons, so that's something else. And of course, remember all the different types of the model of the atom that we spoke about. Okay, now what is radioactive decay? Radioactive decay is when you have nuclei that become so large that they become unstable, and in order to stabilize, they have to spit out radiation. So when they spit out radiation, that is called radioactive decay. Now, in terms of radiation, what they spit, there are 3 types of radiation. You have alpha particles, beta particles, and gamma rays. So out of the 3, gamma is not a particle, it's just an electromagnetic wave. Okay, so what you need to know about those 3 is what it is, how ionizing is it, so how good it is at knocking off electrons of other atoms, how penetrating, how deep it can go into materials, and what it can be stopped by. So an alpha particle, it's 2 protons and 2 neutrons. So if you go back to it, we can see 2 protons and 2 neutrons. That's an alpha particle. A beta particle is just 1 electron. Okay, the reason I wrote helium here is because if you look at a helium nucleus, it has the same number of subatomic particles. So a helium nucleus also has 2 protons and 2 neutrons. So you could say a helium nucleus and alpha particle are the same thing. In terms of the ionizing, alpha particle is the strongest. In terms of penetration, alpha particle is the weakest. And it can be stopped by a piece of paper. Okay, so make sure you memorize this table for all 3 of them. Now, alpha decay. So alpha decay is when an unstable atom releases alpha particles. So for example, what you have to do is the following. You have your element, your nucleus, that's unstable. When it releases alpha particles, it breaks down into a smaller nucleus, and also some alpha particles are released. So the rule is this. They might ask you to write down an equation for alpha decay. So the rule is this. You have to take away 4 from the top number and 2 from the bottom, and then you write helium. So for example, here you have X, 100, and 50. So you're going to write a new element, Y, and then you're going to change that to 96, and this to 48. So you take away 4 from the top, 2 from the bottom, and then you write plus helium 42. With beta decay, the rule is you add 1 to the bottom. So if you have X 150, so you do nothing to the top, so that says 100, element changes, and you add 50, you make that into 51, and then you write beta 0 minus 1. Okay, and you should see that the numbers on both sides should match up. So for example, here is 100, here is 100 and 0, so that's 100. Here that's 50 and minus 1, so again that gives you 50. Okay, also if they ask you what happens to a nucleus during beta decay, you say that a neutron has turned into a proton. That is what happens during beta decay. A neutron has turned into a proton, and at the same time an electron, which is a beta particle, has been released. Okay, now, how would you measure the radioactivity of a substance? So to do that, we have to use this machine. This is called a Geiger-Müller counter. And what this will do, this will tell you exactly how much radiation a particular material is releasing. So for example, what you would do is this. So imagine we have these radioactive rocks. You take your Geiger-Müller counter, you measure it, and it will tell you the radiation, and it will tell it to you in units of becquerel. So becquerels, 1 becquerel means 1 decay is happening per second. If you have 100 becquerels, that means there are 100 decays happening per second. So decay means radioactive decay. Again, this one therefore is more radioactive. So again, it will say to you the becquerels. Now, we know that over time, as the atoms decay, the remaining number of radioactive particles will begin to reduce. So initially, you might have a lot of radioactive particles. However, over time, those radioactive nuclei will begin to reduce as they decay and stabilize. So a half-life is the time it takes for the amount of radiation to half. So, and again, that's measured in becquerels. So half-life, the amount of time it takes for the or for the half of the radioactive nuclei to decay, or you can say for the you can say for the radiation to half. Okay, I think it's better to use this definition, but just to make sure you understand what it means. So with half-lives, they can also always give you calculation questions. For example, here they'll say to you, look, a particle or a substance has 192 becquerels initially. The half-life is 20 minutes. So that means every 20 minutes, that number is halving. How much would you have after 2 hours? Now, to answer this question, we're going to use the following formula. Number of becquerels at the start divided by 2 to the power of h is equal to number of becquerels at the end. So at the start, how many do we have? We have 192 becquerels. 192 becquerels. Now we're going to divide it by 2, and the reason we divide it by 2 is because, of course, it's halving. Now, how many times? What is h? H is total time divided by time for a half-life. So in this scenario, the total time was 2 hours. Let's convert that into minutes first. So that's 120 minutes. So we're going to do 120, which is total, divided by the time for one half-life, which is 20 minutes. So 120 divided by 20 gives you 6. So we're going to do 192 divided by 2 to the power of 6, and that should give you 3 becquerels. So if you leave this material and for 2 hours, after 2 hours later, you'll have 3 becquerels of radioactivity. So that's one way to work out half-life. Another way is by using the graph. So they could give you this graph and say work out half-life using the graph. So what you do is you go to where time is 0 and you work out radiation. So right now it's 800. Then you half it. So 800, half of that is 400. So then you go to 400 and you see that where that goes up to. So that is at 2 hours. So that shows us that the half-life is 2 hours. Now we can do that again by halving this. So from 800, halving it to 200. Again, go to the time and you see there. So from 400 to 200, it took, again, another 2 hours. So that, again, that proves that the half-life is 2 hours. One more time, 200 to 100, 6. Okay, so there you go. You can prove half-life using a graph as well. Okay, now, when you if you notice over here, the graph will actually never hit 0, and the reason it will never hit 0 is because although you're measuring the material, the radioactivity using a Geiger-Müller tube, there's always background radiation which comes into the machine, and that's the reason why it will never go to 0. Now, where does background radiation come from? So there are 3 main places. Number 1, cosmic, so from the solar system, from stars and galaxies far away. Also from nuclear waste products, so if people use nuclear power machines or nuclear weapons, and also from radioactive rocks in mountains. So for example, people who have jobs where they have to, like, let's say pilots are at a greater risk of background radiation than people who are on the earth, like on the ground. A nuclear fallout or scientists that work in nuclear factories, again, are at more risk of background radiation than people who don't. Now, there are 2 types of words that you need to know about radiation. One is irradiation, and the second one is contamination. So irradiation is when the object is near you, but it's not touching you. So the radioactive stuff is just radiating onto you, but it's not actually part of your body. So how you can stop that is by putting the material in lead boxes, using barriers, or remotely controlled arms to operate machinery. And this will keep it as far away from you as possible. Now, with irradiation, remember, the most dangerous ones are beta and gamma. So you don't want irradiation in the form of beta and gamma. If it's alpha, that's not a problem because alpha is not very penetrating. So it can come to your body and nothing will happen to you. But beta and gamma are more penetrating, so they can enter your body. Contamination is when the radioactive atoms are on the object or in the person. So if someone inhales radioactive substances, that is dangerous. So how can you prevent that? Wear suits, wear gloves, and use tongs when you're holding stuff so it doesn't go under your nails. Now, with this one, you want to make sure you avoid alpha particles. So if you get contaminated, you don't want alpha particles to go into your body because they are very ionizing, which means they can damage your cells and it can cause cancer. So it can damage your DNA and that can lead to cancer. If it's beta or gamma that's gone inside your body, that's not a problem because they can easily escape because they're very penetrating.